The last thing we'll look at in module section 4.1 is equations for ionic reactions. This is a concept that will continue to be important as we move on into section 4.2. So I want to spend a little bit of time discussing this, and then we'll discuss it more as we move forward. So many reactions, many important reactions, and in fact, most of the reactions we will be working with in the lab this semester are ionic reactions where we have things that are dissolved in aqueous solution. So you might remember we talked about what that meant in the previous video. Reacting and then forming something that is not an aqueous solution. And this might be, in this case, we're showing a solid. It might sometimes be a liquid. Even it could be a gas. So something in a different physical state than aqueous. We're starting with things that are aqueous, and we're ending with something that is also aqueous. So we want to have an understanding of what is going on with these sorts of ionic reactions. When we write the reaction as we're showing here, it is sometimes called a molecular equation. Now this is a bit of a misnomer. Unfortunately, pretty much all textbooks, including this free online one, are using the words molecular equation. It's been that way since I was taking general chemistry many years ago. And the reason I say this is unfortunate is that there are actually no molecules in this equation. So it's a bit confusing to have just talked about the distinction between ionic compounds and molecules, and then to look at an equation where everything is an ionic compound and we're calling it a molecular equation. So I apologize on behalf of all chemistry teachers for that sort of poor choice of explanations. I'm not going to ask you about a molecular equation, but that's what your book is telling you here. But I think the reason they do this is because we're showing this as if they were molecules, when in fact we know that they're not. When these dissolve, they don't dissolve like this. They actually dissolve as we're showing down here. They dissociate into ions. So the calcium chloride doesn't exist as what we're showing here. It exists as calcium ions and chloride ions. So let's talk a little bit about what we're showing here. You'll notice that when we go from sort of the chemical equation to this ionic equation, we are breaking it apart, and we're breaking it into exactly two parts. It will always be exactly two parts. The parts could be different, but they're always two. One part with a positive charge, so the cation, one part with a negative charge, so the anion. So we have a part with a positive charge, a part with a negative charge. Now when that happens, it's possible there are more than one thing with a given type of charge. In this case, we have more than one thing with a negative charge. We have two chlorides. So when we break it apart, if you have, one type of ion and you have a subscript, the chlorides are not existing as a molecule there. They're existing as the ion. So we put that, basically that subscript turns into a coefficient. Okay. Now, having said that, we go to the very next example, and it is not that way. Okay, so we have silver nitrate. There's actually two things going on here that are different. One is that, so you'll notice that we have a coefficient there. One is that we're starting with the coefficient, and when we break it apart, so we decide where do we break it apart. I said there's actually three things. So the third thing, or I guess the first we would talk about, is that when we break it into two parts, with the calcium chloride, there were only two possibilities, right? Or only one possibility, calcium and chloride. Here we have silver, nitrogen, oxygen. So we might imagine there could be three parts. There's not going to be three parts. Or there's more than one way to break this apart. When that happens, it's almost always going to be, you have a polyatomic ion and you have whatever else. You have the metal, silver in this case. So we break it between what's not the polyatomic ion and what is. So here we have silver is one part of it, and then the nitrate ion is the other part of it. So that's one difference. You have three elements, but we're still breaking it into two pieces. The other difference is the coefficient. So what we do when we break it apart is we distribute that coefficient through to each of the parts. So we have 2 silver, so we put 2 silver, and then the 2 also goes in front of the nitrate. Okay, 2 silver and 2 nitrate. Now what's different here is that when we were looking at the calcium chloride, we had the 2, and we said that becomes a coefficient. The subscript becomes a coefficient. You'll notice here we have a subscript. That subscript is not becoming a coefficient. It is still there as a subscript. And what's different here is that that subscript is a part of a larger thing. It's part of the polyatomic ion. We're breaking apart not into O's, but into nitrates. So nitrate is the larger thing. There are not 3 nitrates here. There are 3 oxygens that are part of the overall nitrate. So that decision to take a subscript and turn it into a coefficient has to be, you have to take into account that you only do that when the subscript is overall the whole thing that you're, taking into. So we're not doing that here because the subscript is only on the oxygen, not also on the nitrogen. And then this last one is kind of bringing that somewhat together between the two ideas here. So again, we break it into 2 parts. In this case, because we have the parentheses, it's very obvious what those 2 parts are, right? So inside the parenthesis is one part, the rest of it is the other part. So this is one part, this is then the other part. Okay, so and then here what we do is we take that subscript and distribute that out, and we have 2 of the entire nitrate. So the parentheses here are a good indication to us that we have that subscript is applying to everything inside the parentheses. So unless you have an element by itself, like the chlorine that we had here, or you have parentheses like we have here, you don't distribute the subscript to become a coefficient. So in this one, we didn't do that for the 3, but we did it for the 2 here and for the 2 here. Also not for the 3 here, right, because that's part of the overall. The other thing I want to point out here is that within this equation, you have 2 reactants and 2 products. And it will be common to have 2 reactants and 2 products where you're basically switching places with things. We'll talk about this in more detail in the next section. But you'll notice that this one is not aqueous. It is a solid. So we don't break that one apart. We don't show this process for the silver chloride because it's a solid. And this is the form it actually will exist as. Okay, so what we can do is we can look at how we broke each of these down, and then we can write that in this form. There's a lot going on here, but this is called the complete ionic equation. Sometimes it's called the total ionic equation. And what we're showing here is we're showing the substances dissolved in water existing as the ions that we know they do exist as. So when we have calcium chloride dissolved in water, it exists as calcium ions and chloride ions. So we're showing the actual form in which they exist. So what we've done is we've basically taken each of these things where we broke it down and we're writing those out. So calcium, 2 chlorides, 2 silver, 2 nitrate as our reactants, and then calcium and 2 nitrate as our product, as well as the silver chloride, which we're showing as a solid, not as aqueous. When we do this, it is important to include the charges correctly, so calcium 2 plus. So if you just put calcium 2 chloride without the charges, 2 plus and minus, if you did not include the charges, it would be incorrect. So the complete ionic equation is showing a lot of information, and what you'll want to be able to do is to be able to go from this sort of chemical equation where we're showing them not showing how they break apart to what we call the complete ionic equation. If we look at this equation, one of the things you'll notice is that it has the same things, some of the same things are on both sides of the equation. So they're basically identical. We'll notice that we have calcium here as a reactant, calcium as a product, and they're plus 2, calcium plus 2, calcium plus 2. They're exactly the same thing. We also notice for the nitrate, so 2 nitrate ions, they're exactly the same thing. We call these spectator ions. And they are not really participating in the reaction itself. They are there to maintain the charge neutrality. So we can't have, so the reaction is basically, with the chloride and the silver, we can't just have chloride ions without a charge in solution without having something to balance them out. But this reaction could take place the same if instead of calcium, we had, say, magnesium or sodium. There are other things we could have here, and this reaction would essentially still make silver chloride. So if we take out those spectator ions, we take out the calcium, we take out the nitrate, what we're left with is the 2 chlorides plus the 2 silvers to give us 2 silver chloride. We can simplify that, the 2's we can cancel out, and we're left with this with the smallest integers possible. Chloride plus silver, chloride ions plus silver ions to give us silver chloride solid. So this is called the net ionic equation, and it's showing just the ions that participate in the reaction, and we don't necessarily care what the other counter ions are with the calcium and the nitrate. Those could have been other things. They could have been sodium, could have been acetate, and we would have gotten the same thing here. So you want to be able to go from the kind of the chemical equation, or algebra calls it molecular equation, to the complete ionic equation to the net ionic equation. And this is something we'll look at in more detail in the next section of this module. But there are some examples here, so please feel free to look at those. So that concludes Module 4.1.